Good morning. This is Dr. Heidelberg, and this presentation is related to robot dynamic analysis. We will open up Module 5 and go to the reference material, and then click on Lecture 5, Dynamics. We open up the lecture so she'll be visible, and the topics that we'll cover is including the definition of robot dynamics problem. We take a look at graphical solutions and analytical solutions to the robot dynamics problem. We'll see how we calculate motor torques and joint bearing loads with solving the robotic dynamics. And then we'll take a look at some system analysis tools that help us solve dynamic problems related to robotics. The basic definition of robot dynamics is a relationship between the forces and moments which act on a robot mechanism and the accelerations and velocities that they produce. Typically, a robot mechanism is modeled as rigid body system. Each body is related to one of the links of the robot, which is connected to another link through joints, and there are internal forces and torques that need to be solved for in order to determine the relationship with them and the resulting acceleration of the links all the way to the tool center point where the point of interest is located. The basic equations which will be used are Newton's law, which says that the summation of all forces acting on a rigid body equals to mass times acceleration, and this is being represented in inertial frame, and also Euler law for the rotational motion, which says that the moment of inertia of the rigid body times its absolute angular acceleration equals to the summation of all the torques which are acting on a rigid body. This is the Newton-Euler formulation, which we will use in this semester. Other formulations include the Lagrangian formulation, which we will not refer to in this course. This represents the basic definitions of the various parameters and variables related to the dynamics problem. We will define the link inertia, the mass, and the moment of inertia. The mass is fixed. However, the moment of inertia depends on the reference frame that we will be describing it. We'll take a look at this in a little while. Then the link position is described as RC, the location of the center of gravity from a certain point. You see this is a vector starting at this point all the way to the center of gravity. And then we have the angular position of that vector in the reference frame, which is fixed to the previous link. So this is theta, and we define the angular velocity as omega. Counterclockwise is defined in our right-hand rule as positive for both omega and alpha. Both have to be represented in radians per second or radians per second squared units. We have link acceleration, which is the angular acceleration, and also the linear acceleration. We have the gravitational acceleration, g, acting at the center of gravity. We also have external forces acting on a link. One external force is the force that the either that the environment is acting on a link or the next link is acting on this link of interest, and this is Fk. And we also have the reference of the force of the base on the previous link acting on this link over here at this joint. We are interested in finding the torque at this point. This is the motor torque. We'll have to find that in order to size the motor in order to provide the motion, required motion for that link, and also the reaction at the joint of the forces of the other links, and that is in order to size the bearing joint, whether it's linear or rotary, for the desired life of the robot. The dynamic forces and torques on the links are related to acceleration. We have a centrifugal acceleration, as we see in kinematics, omega cos RC, where these are the absolute angular velocities of this link in inertial frame. We have the tangential acceleration, which is alpha, the angular acceleration times RC. This is the magnitude and the direction. This is cross product, and the direction we see in 2 dimensions will be, if this is, for example, alpha, then the tangential acceleration will be in the direction of alpha, and the centrifugal acceleration will be from the center of gravity into the point of rotation. Gravitational acceleration is in the direction of gravity, and then the inertial force is defined as the negative of the inertial, of the acceleration of the body. So if the total acceleration of the body is the radial acceleration or centrifugal acceleration plus the tangential acceleration as a vector, and we multiply it times the mass, then the inertial force will be negative of that quantity, minus m times the total acceleration of the center of gravity. The inertial torque is equal to the negative of the moment of inertia times the absolute angular acceleration, and then the force of gravity is mass times the acceleration of gravity, and then we have external forces acting on the joint where another link is connected or the tool center point is connected, and we have also external torque of the base or a motor which is acting on the link. The equilibrium equations according to Euler and Newton is that the summation of all the forces is equal to 0, and this is including the inertial force, which has a minus sign here, and a Euler equation summation of all the torques, including the inertial torque, which has a minus sign, must be equal to 0. So see that for this rigid body diagram, summation of forces includes the force of the base on a reaction plus the force of the gravity plus the force of inertia plus the force of the next link acting on this link, all have to be equal to 0, where the inertial force is minus m times a. And the Euler equation, summation of all the torque equal to 0, means that the motor torque over here, T0, plus the inertial torque, plus the torque of the next link acting on this link, plus the torque of the force of reaction at this joint acting on the center of gravity. All these, by the way, are done on the center of gravity such that the moment of the inertia force is going to be cancelled. And we also have the moment of Fk on the center of gravity, which is rk times fk. So moment of any force times a point is r cross that force. And all of that has to be equal to 0. We can solve it analytically. We can solve it also graphically, and we'll take a look at these two systems. This is an example of a more rigorous way of formulating what we just discussed. It's taken from a reference over here of an MIT EDU. You can click on that and see the entire description. We thank MIT for these contributions, and we will refer to it as a basis to understand how we develop the dynamic equations for robots. This is probably the most exciting field in robotics, and probably the one that would differentiate engineers in a way that the capability to understand the sources of dynamic disturbances on various robot links and the effects on acceleration, velocity, and position. So we'll give it a shot and try to understand what this diagram is showing us. It's basically the same as before, but more rigorously derived. So we'll start with an inertial frame, which has an origin at 0. And then we have a body fixed frame to the previous link, which is I minus 1. It's why we call it O. I minus 1, and this is the link I, and we have another body fixed to this link, which is OI. So this is the center of the body fixed coordinate to this link, and this center of the body fixed coordinate to the previous link. Now, on this link, we have a center of gravity, and we have vectors. We have a vector from this origin to this origin, which is defined as r from I minus 1 to I, and starting here and going here. And then we have a vector from this origin to the center of gravity, which is Ri going to Ci. This is the center of gravity of this link. We also have a force exerted by the previous link, I minus 1 on I. We call it F I minus 1, comma I. And we also have a torque from the previous link acting on this link at this joint, which is N I minus 1 I. And we have that over here, and all these signs are according to the right-hand rule. Then we have a torque of the next link, which is I plus 1, acting on I. Now, you see that the torque that I plus 1 is acting on I is the opposite, according to Newton's first law, to the torque that I is acting on I plus 1. That is why we have a minus sign here. So this is minus the torque that this link is acting on this link will be the torque that this link is acting on this link. And that is what we intersect in the equilibrium equations. Similarly, we have the force that the next link, I plus 1, is acting on link I, which is equal and opposite to the torque that this link is acting on the next link. That's why it's minus Fi, comma, I plus 1. Then what we have over here is the force of gravity. We have the gravitational direction and the mass. And we also have an inertial, a moment of inertia, which is expressed in the body fixed coordinate system. And it will be changing with respect to the inertial frame. And we'll see its effect in a few minutes. And we have the velocity, absolute velocity of the center of gravity, a vector. We have the absolute angular velocity as a vector. And we also have the absolute derivative of these velocities will be the angular acceleration and this will be the absolute derivative of this vector will be the angular acceleration. So this is pretty much an explanation of a general way that we can analyze a specific robot link, and this is true for any link. So the robot may have 6 or 7 links. We start with the one that we know some of these variables, and we solve for the unknowns, and then we carry it over all the way to the base, and on the way we can solve for the reaction forces at the joints as well as the moment at the joints, which will dictate the motor torques that are required in order to drive that robot. Let's take a look at the equilibrium equations. So the first equilibrium equation says that the summation of all forces acting on this link equal to 0. So let's see what these forces are. First we have Fi minus 1 on I. This is the force that the previous link is acting on this link, minus the force that the next link is acting on this link. So this is this force coming here. Then we have the force of gravity, m times g. And then we have the inertial force, which is minus m times v dot. And this is the velocity, the derivative is v dot, and this is the summation of all forces acting on this link. We go now to take a look at the next slide, which describes the inertial moments and the total moment that acting on a CG. But before that, let's just take a look at how the inertial matrix or inertial tensor look like. So this is a matrix, and this matrix is fixed in a body fixed coordinate system, and it will vary depending on which axis we will choose. But basically, whatever axis we choose, typically it's the center of gravity, XYZ in the center of gravity. Then this term over here says that this element is the integral over the entire rigid body of a small element mass, which has a volume of dV times the gravity, so that's the mass. And we take that mass and we multiply times the distance to the x-axis squared. And this summation tells us it's like the Pythagoras theorem. This is the hypotenuse, and the squared is the distance to the x-axis. And similarly, this is the distance to the y-axis, and this is the distance to the z-axis squared. And these are the principal moments of the rigid body in the XYZ coordinate system. If the XYZ are lined up along an axis of symmetry, the cross element, which are similar, these two elements are the same, these two elements are the same, these two elements are the same, so it's a symmetric matrix, they will become 0, and all we have up is the principal moment of inertia with respect to each one of the axes, and all the other ones will be 0. If it is not along the axis of symmetry, then we will have these cross products. We should also mention in a previous slide that if we are looking for a moment of inertia about an axis other than the centroid, such as an axis about the center of rotation, then we have to use the parallel axis theorem that says that the axis, the moment of inertia about any axis which is parallel to the axis of symmetry or axis of the body fixed coordinate system is equal to the moment of inertia here, I, equals to the moment of inertia about this axis plus the mass of the rigid body times this distance between these two axes squared. So this is the parallel axis theorem. So back to our moment equilibrium equation for the same rigid body. We now take the summation of all the moments which are act of on this element, and that's quite interesting to see how it's being derived. Not that complicated, but it has some interesting new element that engineers should be aware of. So starting with the moment that the previous link is acting on this link, it's n I minus 1 on I, this vector here. And then we have the moment that the next link is acting on this link. This is minus n I minus 1 to I plus 1. So this is the negative, as we explained earlier. And then we have the moment that this force of the reaction is acting on the center of gravity. Now, what is this moment? This moment is the radius vector from the center of gravity here cross this vector that we have over here. But what is the radius vector from here to here? It is the negative of the sum of this vector plus this vector. The sum of these two vectors is a vector from here to here. So a vector from the center of gravity to here will be exactly the opposite. This is why we have a minus sign here. Minus the sum of these two vectors cross with this vector will give us the moment of this force about the center of gravity. And then we have, in a similar fashion, the moment that this vector minus r comma I plus 1 having on this vector. So this moment will be this cross product of this radius arm from here to here, which is minus the radius arm from here to here, cross with this vector. And this is exactly what we have over here. Minus I comma ci, which is a vector from here to here, cross with this vector. Then what we have is the inertial torque, which is I times omega dot. This is the angular acceleration, absolute angular acceleration of this. And now, because of the change of the moment of inertia when we rotate this body with respect to inertial frame, we have to add in a derivative of the momentum, angular momentum, the element of omega cross the angular momentum. So the angular momentum is I times omega I, okay, matrix times a vector, and then we cross it with omega I. And this element over here, we still have the minus sign. This whole term is the inertial moment. This term over here is so-called the gyroscopic torque. And this is an element that many times is overlooked, but it is similar on a way to the Coriolis acceleration that we saw in a linear formulation, in a kinematic linear formulation. Depending on the coordinate system that we use, it may pop up. Many times it's being cancelled when we choose the right element of the moment of inertia. Here's an example of how we use the previous general formulation, again taken from the same source. We can derive the solution both analytically and graphically to a articulating robot where we have all the various elements of inertia for each one of these links. This time they are connected, the position, the length of the link, the mass, and we could start by looking at the free body diagram of the first link. The first link will be having summation of forces and moment equal to 0. Summation of forces include the force of the base acting on the first link, F01, minus the force that the second link acting on link 1, which is minus the force at link 1 is acting on link 2, plus the gravitational force minus the inertial force, which m, times the acceleration, which is v dot, or acting at the CG. So all of these must equal to 0. And when we look at the equation of moments of the first link, we see that the motor torque, or the torque of the previous link acting on the first link, is N01, plus we have the torque that the second link acting on this link, which is N12, and we have the torque that the reaction force is acting on the center of gravity of link 1, which is R1 to C1 cos F1, and we have also the torque that this force is acting on the center of gravity, which is minus this vector arm cos F01, and then we have minus the inertial moment of inertia of link 1 times the angular acceleration of link 1. So these are the equations of equilibrium of first link, and we write similarly the equation of the equilibrium for the second link. So on the second link we have the force at link 1 is acting on link 2, plus the gravitational force on link 2, and we have minus the mass times the acceleration, or the inertial force acting on link 2, all equal to 0, and the summation of moments of link 2 is the torque that link 1 is acting on link 2, plus the torque that the force F12 is acting on link 2, and we have the inertial torque I2 times the absolute angular acceleration of link 2. So we have here four equations, four sets of equations. They are vector equations, so they are in x, y, z. So altogether, each one of these are three equations. So we have 3 and 3, 3 and 3, 3 times 4, 12 equations, and we have to solve them. It may get involved when we solve them analytically, because there's a lot of matrix transformation here. All these equations hold true only in inertial frame. However, some of these elements, such the inertia or the radius, are conveniently expressed in body fixed coordinate system. Therefore, we have to transform each one of these elements from its own coordinate system after we do it into the inertial, and that may be a little bit complicated. That's why we many times refer to graphical solutions in order to either validate the analytical solution or just find a solution. This is basically the formulation as we explained it before for the same link, and as we expand it using the various transformation metrics, you see that the expressions for even for velocity, not to mention acceleration, become rather complex, including sine and cosine, and also all the length and the inertias and the accelerations come into the expansion of these elements. We could try to understand some of these expanded variables. For example, when you take a look at the motor torque acting on this link, you see that it has many parameters that define both links, not just the first link, and it is multiplied times the angular acceleration of the first link, plus a similar expression times the angular acceleration of the second link. And then there is another, so this is basically like the equivalent to the tangential acceleration, effects of tangential acceleration on the motor torque, the torque of this tangential acceleration. And then we have also the centrifugal effect where we see over here velocity square times h, and h again is a complex expression of all the system parameters. And then we have something which is equivalent to the Coriolis acceleration or gyroscopic effect of the two angular velocities, and then we have the torque of gravity. And similar to the second equation, things get quite involved, and that's where either a software program that helping us to do dynamic analysis as well as graphical solution help us to solve certain problems related to a robot, whether they're articulating or Cartesian. Of course, articulating, they have all rotating element are the most complex to solve. When we apply solutions to practical problems, whether we develop the equations ourselves or use existing analytic solution, it is always important to check the model against simple cases such that we apply only gravity and we eliminate all the accelerations, and we see if the results make sense. Once we validate the solution, we can run parametric analysis to find which parameters of the systems the robot is most sensitive to, and then we could try to optimize for the required problem the selection of all of these parameters. Here's an example how we take an existing solution. As we saw earlier, we translate that into Excel spreadsheet, and we use some known formulation for moment of inertia. For example, for a prismatic element, we have the moment of inertia along the principal axis is equal to mass divided by 12, and then divided times the sum of the square of the width and the depth of that element. So this will be the moment of inertia about a certain axis. We use this formulation in order to sometimes simplify the geometrical expressions of actual robots in order to find estimated value for our analysis. So once we resolve the equations within the Excel spreadsheet, for example, we could simplify by putting zeros on some of the dynamic variables and check the results and see if they make sense. And then once they make sense, we could use the model to do some sensitivity analysis. For example, take a look at the result of motor torque as a function of link position. That may help us to optimize the configuration of the robot, of where it does pick and place in particular applications, and optimize the motor size. As an appendix to this presentation, we have the derivation of velocity and acceleration of a point on a rotating coordinate system. We will not repeat that. It was part of our kinematic lecture, but it's shown over here as a process. We have several ways of doing it. One formulation does not include the Coriolis. Another formulation does include the Coriolis, exactly identical, and I recommend that the student go through that derivation and try to understand that process. We also have here an example that showing how we may use MATLAB We saw earlier how to use MathCAD. We also have MATLAB in our laboratory, which is available to the students. MathCAD could be downloaded free for life from the internet. This is a simple example that shows a single link which has various parameters, and we go also through the process of coordinate transformation, and we're interested in this particular case, given the angular velocities and acceleration, mass and inertia, we're interested in the reaction force and the motor torque, so we can go through that derivation and write each one of these vectors, write the equilibrium of the both forces and torques. We see over here that the summation of forces is the inertial force plus the gravitational force plus the reaction force, and then similarly for the torques. And then we can go to MATLAB, define all of these variables and do the cross product as needed, define the matrices and find the forces, reaction forces, and also the motor torque, and according to the formulation. And then we can also use a graphical solution method, which is also described in some online tutorials for the problem, and then compare it to the analytical solution. So in this example, we see that the centrifugal acceleration is from this point towards the center of rotation. It's mass times this acceleration. This acceleration is this lever arm times omega squared, because it's two-dimensional, and the tangential acceleration will be in this direction, and this is this vector arm times the angular acceleration, and then we have the force of gravity in this direction. So we could, when we write the equation of equilibrium, we see that the reaction force equal to plus, we move all these elements to the other side, and the reaction force is m times a, total acceleration, minus the transformation from we do all of that. For example, we resolve that in the they're all in inertial frame, but we can resolve it into any other coordinate system. Here, for convenience, we resolve it into the body fixed coordinate system, and therefore we have to transform it, the mg, which is defined in the inertial frame, into the body fixed coordinate system with this matrix of transformation, and it has a minus sign here when we move it to the other side. And then when we draw the diagram, you see over here that this is the centrifugal force towards the center of gravity. This is the tangential force. This is minus the gravitational force. The sum of all of them is the total reaction force. And then we can resolve it into the body fixed coordinate system, and we find over here minus 101 millimeter, and this is we check that with the analytical result, which is 100.5, very close. And then in the y direction, it is over here 92 positive, and that's what we found out in MATLAB is 92.4. So this concludes our discussion of the dynamic analysis of robot, and we will have more exercises, tutorials, and also lab experiments related to it. Thank you.